So let us now discuss about the homework problem given last week. Uh, we were calculating the proton affinity of methyl anion, and we have done Hatter's-Fock, PB and B3 lip. So we are going to do the homework problem was M062X and MP2 and also the B2P lip. So we will do the calculation now and see how the values actually changes with the change of functionals. Let us go to the Excel sheet. It's my proton affinity. Now let us go to M062 62X. So let us go to the week 6. We can take any of this. So this is CH4PBE, and this now I can change it to M06 2X. Remember, it's also a hybrid. It's actually a meta GGA hybrid. So I need to use Rij cos X, and let me save it. Let me write it as M062X dot INP let me run the calculation. So open terminal, let me increase the size a little bit. So it's Orca M CH4 also let me try the making the corresponding input file for the anion. M062X. Remember, it's very easy to make a mistake between 0 and O. This is 0, not O, so be careful while writing. So let me do the Rij cos X. Save as CH3M M062X dot INP. My previous calculation is done. Let me submit the one. CH3M by the time this one is running, let me open the previous output file. This is my final single point energy. The CH3 anion is also done now. So, let me open the output file. So, you can see that the agreement with the acceptable value is slightly better in M062X. You may see that with comparison to other software package like Gaussian, the number of Minnesota functions implemented in Orca is actually slightly smaller. It is actually not smaller, they are just not available in form of a one liner keyword. You can actually get to any of the Minnesota functions by changing the parameter, which is possible in Orca. I will not discuss this in this course. So, if you want to get any of this Minnesota function, you should go to Orca manual and you will see how the individual parameter, the exchange correlation parameters can be modified to get to the proper Minnesota functionals. So, at least in this case, this is better than B3 Now, let us try MP2. So, this one let me save it as CH. I wanted to do the, okay, any of them can be done first. Let us first do the methane. INP. Okay, you may ask that is a quadruple zeta quality basis set good for and any calculation for in MP2? I would say that I would love to do complete basis set extrapolation, but quadruple zeta should be fine unless you are looking for spectroscopic accuracy, which is anyway not possible to get in calculations. Quadruple zeta for most of the times is fine. If you are in two minds, then you should do the extrapolation. It is very unlikely that CBS results and the quadruple zeta result will change qualitatively. It may change quantitative numbers, but not qualitatively. So, CH for MP2, and let me run the calculation. So, it is Orca CH4 MP2.inp. It gives an error and it says that RIMP2 needs an auxiliary basis set, but none is defined because we have not given the corresponding auxiliary basis set there. So, there are two options. There is no auxiliary basis set for def to QZ VP. So, you have to use either def to QZ VP P/C. This basis auxiliary basis set is there. You can open the Orca manual to find out what auxiliary basis sets are available, or you can use AutoAux. But generally using the standard pre-optimized auxiliary basis sets are good idea because the basis set dimensions is generally smaller. So, now we will save it again and this time it will run. So, let me make the input file here also. So, now this is RIMP2 . I should not forget to give the def to QZ PPP/C, the auxiliary basis set. maybe a good idea would have been to give some more memory. So, at least here in this case I can define max score 2000 MB. Save it and let me run it again. So, by the time it runs, so this is for the methane. I should write this is MP2. So, now this one is also done. The final single point energy. So, at the MP2 level, the value is not anyway qualitatively better than the B3 to the power M062x. If you are interested, you can try a CBS and see how the numbers actually looks like with the CBS. Of course, we have still not done the B2 PLIP. So, let us try do B2 PLIP, and advantage if you have an MP2 input file, the B2 PLIP is almost same. So, I have to just write it as CH4 B2 PLIP. This is our B2 PLIP. Let me make for the anion also the input file. CH3M B2 PLIP. In place of RIMP2, I should write B2 PLIP. So, we have discussed that the double hybrid function actually has same computation cost and similar basis set dependence as the MP2. So, this one is done. Let me submit the CH3M. So it may be a good idea to look at the double hybrid output file, because we have not looked into any of the double hybrid output file. You can see that it will do the DFT with the standard grid settings, and it is used of course cos x to solve the DFT part, and it says what are the parameters which is used. It's so this is your normal DFT, and after your normal DFT is done, it actually has an MP2 calculation, and it's freezing the core, because in correlation method we have seen that it's quite common to freeze the core, and these are MP2 correlation energy, and then it adds it to the final single point energy, which actually is plotted here. And for the anion, here is the value. This is the final single point energy. I should be careful to copy the minus sign. So this also gives you a similar answer almost to this DFT functional. Maybe it's a basis set artifact, because we have not went into complete basis set limit. So maybe you can try to do it yourself to check how the MP2 behaves in the complete basis set limit, and maybe try some DLP, CCSDT numbers. Okay. The other thing we have discussed, that the double hybrid functional does not have the problem with dispersion. So now let us go back to that problem and try to calculate the surface with now B2 Blip. Okay, let me open it. Let me go to the plot. I can delete this one for the time being. I can go to scan B2 B3 lip. I can save it as scan B2 blip. I need to remember that I need to change the B3 lip to B2P lip. I am using Ri. So, I need to give an auxiliary basis. In this case, I will give auto aux. Scan B2P lip dot INP. Now, let us run the calculation. So, it is ORCA scan B2P lip just run the calculation, and by the meantime I can prepare the input file for the single argon atom. This was my second homework problem where I was discussing about argon dimer. So, now it is done, and let me at least make the input file. I can make this one, maybe I can save it as AR B2P lip dot INP B2P lip RI BP2P lip because I am using RI for the correlation part. I should use auto aux. Let me save it, run ARP2P. So, let us first went into the trajectory file. It's not copied properly. Next, next. Let me copy it. I put it here. I put it. Yep. I go to the individual energies. This is my final energy. Energy of the dimer minus twice the energy of the monomer. This has to be minus. Now let us plot it. more line chart. So, although you can see that the binding is small, uh, it actually gives us slightly stable structure of AR2 than isolated AR, and which is different from the completely unbound potential energy curve obtained in the case of normal B3 lip. So, using the MP2 correlation energy actually is helpful to get a slight binding. Of course, what is important to notice here is that the binding is not so much, it is not so much as close to the what you obtained with the D3 correction. So, maybe a good idea is to use the D3 correction even with the double hybrid also, and generally B2 PLIP is also used with with the D3 correction. So, you may repeat the calculation with the D3 correction and see how the potential energy curve looks like.